Now, last question, number 5. A bottle contains 6.15 molar solution of CH3COOH, which is acetic acid. Let's get A. Write the balanced and correct equation for the dissociation of CH3COOH in water. So basically it wants us to write the correct dissociation equation for acetic acid. Well, in order to write the correct one, we have to figure out, do we have to use a single-headed arrow or double-headed arrow? And that all depends on, is the acid a strong acid or a strong base, or a weak acid or a weak base? In this case, we know it's an acid, and then we have to recall our 7 strong acids, and acetic acid is not one of those strong acids, which means it is a weak acid. So we're going to have to use a double-headed arrow, which means that it's an equilibrium reaction. So let's do this real quick. We understand that acetic acid comes from the ion of a hydrogen ion and an acetate ion. So let's write this out. CH3COOH, which is the acid. We use the double-headed arrow, and it's going to dissociate into CH3COO with a -1 charge and a +1 charge for the hydrogen ion. Now, another way we can write this, because acetic acid is not always written as CH3COOH, sometimes it can be written as HC2H3. Ooh, how did that end up like that? H3O2, and we can write it the same way, except for now we are in a much more familiar form of hydrogen ion coming first, and then the acetate ion coming right afterwards. So these both are balanced, so it's either the top or the bottom one, whichever works. All right. Now, let's look at the next one. If the bottle holds 4.2 liters of solution, how many moles of acetic acid are dissolved in the solution? Well, this is a simple matter, because we are going along with the equation of molarity equals moles over liter. And since we know the concentration, which is 6.15, and we know our volume 4.2, we just need to plug it into the equation, which means 6.15 molar equals x moles. Ooh, why did that disappear? X moles over 4.2 liters, which then we multiply 4.2 on each side. Alright, these can divide out, and then the units divide out, leaving us just moles. And when we do that calculation correctly, we should have 25.83 moles of CH3COOH. And this is how much is dissolved in our solution. We do have to kind of assume 100% dissociation in these type of questions. All right, so let's go on to our next one. Calculate the pH and pOH. Now, looking at this dissociation reaction, what do you think we can calculate first? Yes, the hydrogen ion indicates that we can calculate our pH first. Now, a hydrogen ion concentration, because it is a 1-to-1 ratio, because it's a monoprotic acid, tells us that we can keep using the equation pH equals -log of concentration of hydrogen ion, in which we've established from up top, because of monoprotic ion, hydrogen ion concentration is the same as the acid, which is 6.15 molar. So all we need to do is plug it right in here. So we have pH equals -log of 6.15. And this leads us to a negative pH of -0.7889. So this is our pH. So if we know our pH, we know that pH plus pOH is going to equal 14. And if we know our pH value as right here, we will be able to figure out that pOH equals 14.7889. And this is our pOH value. All right, let's move on to our actually, we do have 2 more questions. So let's look at number 6 and 7. All right, number 6, a solution has H plus, so the hydrogen ion concentration value of 5.99 times 10 to the power of negative 6 molar. What is the hydroxide value? Now, the hydroxide concentration value, there are multiple ways we can go about this. However, the easiest one is understanding the relationship in which the concentration of the hydrogen ion and the hydroxide ion, when they are multiplied, they must equal 1 times 10 to the power of negative 14, because our pH scale is a logarithmic scale. So let's write that equation down. Concentration of H plus multiplied by concentration of OH minus, so the hydrogen ion concentration multiplied by the hydroxide ion concentration, will always equal 1 times 10 to the power of negative 14. All right. Well, molar, because we're looking at concentration, right? So, okay, well, let's solve this out. We already know our hydrogen ion value, so all we need to do is plug it right in, which means 5.99 times 10 to the power of negative 6 molar. Actually, yeah. Multiplied by the concentration of hydroxide ion equals 1 times 10 to the power of negative 14, right? So in this situation, all we need to do is divide each side by 5.99 times 10 to the power of negative 6 molar. And we're going to do this. And when we do that math and we put that into the calculator, we should be able to get concentration of hydroxide ion as 1.669 times 10 to the power of negative 9 molar. That is our final answer. Okay. All right. Our last one. If a solution has a pH, concentration of hydroxide ion value of 7.42 times 10 to the power of negative 5 molar, is the solution acidic or basic? Well, if we have concentration of hydroxide, we can definitely figure out pOH. So pOH equals negative log of concentration of OH ion, in which we can just plug this value right there, which gives us negative log of 7.42 times 10 to the power of negative 5, and this gives us a value of 4.130. Now, pOH scale. If you have had a lot of practice, you will immediately know what the pOH of 4.13 would be in terms of acidic or basic or neutral. But not many of us, or not many of you, can maybe used to this scale. So we would probably want to convert this into a scale that is easier for us to understand, which we're a lot more familiar with the pH scale. So with the pOH, we know we can figure out pH because we keep going back to that equation, pH plus pOH equals 14. So if we know that the pOH is 4.130, we can calculate that the pH is 9.870. Now, a pH of 9.870, that is above 7, which means our solution right here is a basic solution. Or we can say it is an alkaline solution. And that wraps us up. Hopefully this tutorial was helpful for you all.